Okay, we're going to do section H3N. We're going to talk about vector equations of lines, vector form, and parametric form. This is probably one of the more important lessons in this chapter. So look at investigation number 11. Consider the line that passes through point 1, 3 and is parallel to vector B. So what we're given here, it passes through this point. So this is our position vector. It's a position on our line right there, right? And this is our direction vector. Okay, so it's parallel to this vector, which means the direction on the line that we're moving, it's going to go 2 to the right and 1 up. So for here, from A, I'm going 2 to the right, 1 up. 2 to the right, 1 up. So explain why the position vector of C can be written like this. So, so basically, if I'm starting from here, and so 1, 3 is our starting point, and in our 2, 1 is our direction vector. If I multiply our direction vector by 2, that's going to make us go over, instead of 2, 1, it's going to make us go over 4 and 2. Okay, so 2 is our scalar that gets multiplied by the direction that takes us all the way to C. Write down similar expressions in the form A plus TB. So we're going to be writing it like this much of the time. So R, which is our equation of the line for our vector, equals A plus in our assignments today, it's going to have a lowercase t. In some of the IB test questions, they might have this lambda, and then sometimes I've seen the letter mu, but it's some symbol here that represents time. Okay, so we've got our position vector we start off, plus our time position, and then our direction vector. So we multiply our scalar, which is time, times our direction vector, which changes the length and where we are on the line based on the time. As time moves on, we move further or closer to A based on this value here. So write down similar expression for A plus TB. So if we're wanting to go to A, we start off at 1, 3, and we don't move left or right or anything, we just stay right there. That's why our T value here is 0. Okay, our T value is 0. For B, we're going over 1, so we're going 2 to the right, 1 up. So our T value here is just 1. To go to C, we're going over 4 and up 2. So here the T value is 2. And to go to D, I'm going to go, instead of the right 2, I'm going to the left 2 and down 1. So my T value is -1. Okay, so can you deduce, what can you deduce about the position vector of any point on the line? So any point on the line, I'm going to be using this this equation for for our vector equation. So our position vector, the position is going to stay the same, 1, 3. Why will this not be true for any point not on the line? So if we have a different position vector, then and we still go in that direction, we won't be able to stay on the line. So a point that is not on the line, then it might not go through the position vector. Okay. So let's move forward. So show that A, B, C, D can also be written in the form 3, 4 plus S times, so they've changed my position vector, and we've also changed my direction vector. So for all of these points to stay on this line, but with these parameters, 3, 4 has to be on the line, which if we go to the picture, we can see that it is. 3 and 4 is right there. That's on the line. And -2, -1. So that means -2 means I'm going to the left 2, and -1 means I'm going down 1. So that is on the line. So if I have this new position vector and this direction, so there's our position vector. We have this new position vector, and this position is on the line. And we have this direction vector. It's the same as the other direction vector, except it's multiplied the top and bottom by -1. The other one here was 2 and 1. Now we're at -2, -1. So it's parallel. It's just going the opposite direction. So because this point is on the line still, and this direction vector is parallel, then we can use this equation to find points A, B, and C, and D also. Okay, so what is the vector equation of a line in symbols? So the A value here is our position vector. This value here is time. And as I said, that sometimes on this textbook, they're going to use a lowercase t. And then B is our direction vector. Okay. So when we write it like this, our vector form, okay, so if we've got a line passing through this point in the direction of this, it can be written in vector form. So instead of writing R, it's okay to write X, Y, and Z. Okay, and if I'm writing it in vector form. So once again, we've got our position vector, 1, 2, 1, and we've got our direction vector of 1, 8, -2. Okay. Now, if I want to write this in parametric form, means I just take each row and I can write them separately. So this top row is x equals 1 plus t times 1. The middle row is y equals 2 plus 8 times t. The bottom row is z equals 1 plus or minus 2t. So when you're writing in parametric form, it's kind of the same as vector form, but I'm just writing each row separately when I'm writing it in parametric form. This is just the same thing as here, but I wrote it larger so that it's in my notes and I can see it better. Okay, and we can even write this in coordinates. I could write this in coordinates as 1 plus t, comma 2 plus 8t, comma 1 minus 2t. I can write it in coordinates. Okay. Okay. So let's look at example 11. Okay, find the equation of the line that passes through this point and this point. So the first thing I need to do is I need to figure out the direction. So to figure out the direction vector, I found I found out vector AB, because if it passes through these 2 points, I can find direction vector AB. So I take my B values of 2, 3, -1, minus my A values of 1, 0, 2, and then I can figure out my direction is 1, 3, -3. And I'm going to put that direction right there, 1, 3, -3. Okay, because we're using this formula, and that's my direction. Now, position it truly doesn't matter. I could put 1, 0, 2 here. I could put 2, 3, negative 1 here. It doesn't matter which position I put in because both of these positions are on the line. It doesn't matter which one you put here. Okay? Okay, determine whether or not 3, 6, negative 4 is on the line. So basically what I'm doing here is I'm taking this value, um, uh, let's use a highlighter that will, so I'm taking this value, the 3, 6, and the negative 4, and I'm making r equal to that. I'm letting r equal to that. So I'm rewriting this equation, but instead of r, I'm writing 3, 6, negative 4. So we're going to see if this is true. So is 3, 6, negative 4 vector equal to 1, 0, 2 plus t times my direction vector of 1, 3, negative 3. So I check that out to see if it's true. So if I have 3 equals 1 plus t, so if I have 3 equals 1 plus t, subtract 1 on both sides, that means t is 2. Let's check the middle line. 6 equals 3 times t. So 6 equals 3 times t. So if I did divide that by 2, I also get the t value of 2. And the bottom one, 4 equals 2 plus negative 3 times 2. So, and that works also. So if I plug in 2 in for t, I'm going to get the same answer for all of them. So if I plug in 2 in for t, I'm going to get 3, 6, and negative 4. So since we get the same answers, green answers for all of these when t is equal to negative 2, we know that it works, that this point is on the line. Okay? You might want to hit pause to think about that some more. Okay, find the angle between the line AB and the line, and this line here. So, so the first thing we need to do, remember in a previous handout, we've got this formula cosine theta equals the dot product of the two vectors divided by the magnitude of one vector and the magnitude of the other. So that we're trying to find the angle through the between the lines through an A and B and this other line. So so line AB has a direction vector of 1, 3, negative 3. So this is the direction vector for line AB. 1, 3, negative 3. This is the direction vector for line AB. This here is the direction vector of this other line. This is some other line. Okay, so we've got some other line. So we're going to do the 1, negative 1, negative 2, and 1. So I'm going to do, in order to find this angle, I need to do the dot product of these two vectors. So 1 times negative 1 plus 3 times negative 2 plus negative 3 times 1. Okay, and then I end up with negative 10. I figure out the magnitude of this first one. So square root of 1 squared plus 3 squared plus negative 3 squared, and we end up with square root of 19. And then this other vector, negative 1, negative 2, 1, I find out the magnitude of that, negative 1 squared plus negative 2 squared plus 1 squared, is going to give me the square root of 6. And so now I plug this into my equation here. So cosine theta equals negative 10 divided by square root of 19, square root of 6, and then I get this value. And I get theta equals 159. So I can write my answer as either 159 or 21 degrees. So the angle between the two lines can either be given as an obtuse angle or the acute angle unless it otherwise specifies. So sometimes they may say, what is the acute angle? Or they may say, what is the obtuse angle? Because if I have two lines, let's pretend these are my two lines, it should make sense that I'm either going to get an acute angle or over here I'm going to get an obtuse angle. So you will get two possible answers, and they're going to say, oh, give us the acute one, oh, give us the obtuse one. Okay, reflect. Okay, so how do you find the vector equation of a line if you are given its direction and the coordinates of a point that it passes through? So once again, we're using this formula to find the equation, a vector equation, with its position, the time, and the direction vector. Okay. How do you test whether or not a point lies on a given line? So to test if a point lies on a given line, we let R be that point, just like we did on the previous example. So we figure out what that point is, and we plug that in for R. In this previous example, we plugged in 3, 6, and -4 in for R. Okay, then we solve for T and for the parametric form, and then went to see if T was the same for all parts. Okay, so okay, and the critical thing that we did here was when we were trying to find the angle of two intersecting lines, we found the angle between the two direction vectors. Okay, all right. So you can check your answers. I'll walk you through a little bit. So find the vector equation of the line that passes through these 2 points. So if with this point and this point, I found that our direction vector of 1, -3, and then I picked one of these 2 points, and there's my position vector, and there's my direction vector. Same thing here. Using these 2 points, I found the I guess I called this point A, and I called that point B. So to find my direction vector, I did 4, 2, 0, minus, 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 2, 1, -1. Okay, so that's my direction vector. Here's my starting point. So I picked this as my starting point, and I picked this as the starting point for here. And I could have used the other point as the starting point. It truly doesn't matter. Okay. Let's move this up. Okay. So point A, -2, B lies on the line. Find out what A is and what B is. So I rewrote it in parametric form. X equals 1 plus T. Oh, but instead of X, we have A, right? So I'm replacing X, Y, and Z with A, -2, and B. A, -2, and B. Okay. So, so then I have 1 plus T equals A. I've got 2 plus 8T equals -2. And I've got 1 plus -2T equals B. You might want to hit pause and think about that if you aren't sure again. So using this first equation, I could figure out, using the second equation, I could figure out T. 2 plus 8T equals -2. 2 plus 8T equals -2. So we can solve for T. Once I know T, I can plug it into the first equation. So we know that A equals 1 plus T. And so if I plug in -0.5 in here, I get A. We know B is equal to 1 minus 2T, so I plug in -0.5 in for T, and then I end up with B. Find the coordinates of a point on the line with x coordinate equal to 0. So if I make the x coordinate equal to 0, then I've got 1 plus t. And for making the x coordinate equal to 0, then I have 0 equals 1 plus t. And so that would make, if I subtract 1 on both sides, I end up with t equals negative 1. So if I know that t equals negative 1, I can plug that back into my original equation. My original equation is equal to 1, 2, 1. That's my position vector. And then I've got my direction vector of 1, 8, negative 2. And we just said t is equal to negative 1, so I'm plugging in that value. And so then I get 1 plus negative 1 gives me 0, because they wanted us to figure out this when the x coordinate is 0. Then 2 plus negative 1 times 8 is going to give me that. 1 plus negative 1 times negative 2 is going to give me this. So this is the coordinate when the x coordinate is equal to 0. This is the point, not the coordinate. Okay. All right, 3a. Find the value of s and p when it lies on this line. So once again, I'm replacing r with 2s and p minus 1. So I replaced r with that, and then I rewrote it in parametric form. And then what did I use? I used this top line here. If I have 2 equals 1 plus t, we could subtract 1 on both sides, and we get t equals 1. And then, so now, if I know t equals 1, I could plug in 1 in here. So I have s equals 3 times 1. If I replace t with 1, and so now I know s. If I replace 1 in here, I have p minus 1 plus 2 plus 1. And then I end up with my p-value. Okay. Verify that this point lies on here. So once again, we're replacing 1, negative 3, 8 in place of r. We've got our position of 3, 1, and 2. We've got our direction vector of 1, 2, negative 3. And we're going to verify that this point is on this line. So if I put this in, 1 equals 3 plus t, and I get negative 2. I have negative 3 equals 1 plus 2t, and I also get negative 2. The last line, 8 equals 2 minus 3t, and I also get negative 2 when I've plugged in the 8, the negative 3, and the 1. So since t equals negative 2 for all of them, I've just verified and shown that this point is indeed on the line, since I get the same t value for all 3 equations. Okay, write down the vector AB. The point B is on the line with parameters of t equals 5. So we used a t value of 5. So we've got our position vector of 3, 3, 1, and 2. Here's our position vector. We've got our direction vector of 1, 2, negative 3. And we're trying to find a point when t equals 5, and then we multiply and add these across, and there's my b value. So now that I know my b value, I can find the vector AB. So the vector AB, I'm going to take the 8, 11, negative 13, minus, 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 and my a value, which is, what's the a value? 1, negative 3, and negative 8. Oh, it's from there. Okay. And then we get this. Okay, verify this point lies on both lines. So, what did I do? I made R equal to these values, 2, 1, and 3. So this is the first equation here. This is the second equation here. I rewrote it in parametric form, and I put in the 2, the 1, and the 3 in place of R. And then I did 2 equals 4 plus negative t, and I ended up with the same value of t for this equation. Over here, I plugged in the 2, 1, 3 over here and put it in parametric form, and I get the same value for s for this equation. So because these are the same value and these are the same value, I've verified that this point lies on both of these two lines. Find the acute angle between the two lines. So once again, if we're going to find the angle between two lines, I have to use the direction vectors only. So negative 1, 3, 1. 2, 1, negative 3. I'm using my direction vectors only to find my dot product. Then I find the magnitude of each vector, and then now I can write it in cosine theta equals this value divided by the square root of 11, square root of 14, and then we get this. And we know this is greater than 90, it's obtuse. And it says find the acute, the acute angle. So I have to do 180 minus this value, and there is my acute angle. You might want to hit pause. You might want to hit rewind to hear this part over again if you need to hear it again. Question 5. Two lines are given here. Explain why these are parallel. So you can the reason these are parallel is these this second value, the 2, the negative 4, and the negative 2, this is the same as this, except we just multiplied this equation here by times, or if I multiplied this one here by negative a half, then I get the same equation. I could have simply multiplied this equation by negative 2, right? Negative 2 times negative 1 gives me 2. Negative 2 times 4 gives me negative 4. Negative 2 times 1 gives me negative 2. Anyways, they go the same direction. This is just a multiple of this vector with a different scalar value. The scalar value is the number you multiply by the vector. Okay, verify 1, 9, and 4 lies on the line. So once again, I'm plugging this value in for r and this value in for r. So using this equation here, I'm plugging in, I rewrote that equation, but instead of r, I wrote 1, 9, and 4. Wrote it in parametric 4, I get the same t. Now I take the second equation here, instead of r, I put in 1, 9, and 4, and then write it in parametric form, and once again I get the same value, negative 1, negative 1, negative 1. Okay, since the lines are parallel, that means both, since the lines are parallel, and both have the same point on the equations, this means they are the same line. Okay, well, I'm going to pause and think about that. This is a new word you may or may not have heard of before. Coincident means the two equations have the same line. Okay, let's see if I finish this before the bell rings. Okay, so we've got point A and point B. Okay, so show that A lies on this equation here. So I've got A is 1, 5, negative 6. I put that into this equation here, right? But instead of r, I've got 1, 5, negative 6. And then I rewrote this in parametric form, and indeed I get the same value of s for each one. So, so I've shown that it is on the line. For part B, show that AB is perpendicular. So if it's perpendicular, then that means the dot product is going to be 0. So let's find the dot product of the two vectors. So before I can even get started, I need to find equation AB. So equation A is this, equation B is this. So I take the A and the B coordinates to find vector AB, and then I do the dot product of this vector AB and the dot product, and I've got the direction vector of the original one, and indeed I do get 0 for the dot product, and that verifies and proves that these vectors are vectors are perpendicular. Why on earth did I write the word parallel? Perpendicular. Okay. Okay, is this last question? Yes. Okay. We've got this line. Write down the coordinates of point P. Okay, so point P. There's our coordinates. Okay, point A has coordinates of this. Find vector AP. So I took my coordinates of P, which is 2 plus T, 3T, 1 plus 2T, and then minus, 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 and point A, which is 1, 2, negative 2. Here is my vector AP. Okay, to find the value of T, which the vector AP is perpendicular. So if I take vector AP dot and then this direction vector 1, 3, 2, if they're going to be perpendicular, then the dot product is going to be 0. So I do this times 1, this times 3, and this times 2, and we need to make it equal to 0. So now I can simplify and solve for T. Okay. Use T equals negative 1/14 on the line, and we want to find the point that is closest to A. So we know that happens when the lines are perpendicular. Then the line closest is going to be when we use the value of 1/14. I'm sorry, negative 1/14. Okay, and then question E, the vector between A and the new point. So we've got our new point coordinate here, and we've got point A, and then we can figure out vector, this new vector, and then to figure out the distance, which they've asked, then I can take the magnitude. I hope that helps, and there you go.